Hello, my name is Brant. I'm a first-year PhD student from UIUC. In this talk, I will introduce our ongoing work, Poseidon, an end-to-end system that automatically optimizes floating point programs in compilers. This is joint work done in collaboration with Weimar Stasia, Jan Hugelheim, Paul Hoffman, and my advisor, William Moses. There's a trend in machine learning to reduce precision to increase performance. However, the solution to increasing performance is not decreasing precision uniformly. Since some operations will give a bigger bang for your buck and can be changed a lot, and other operations need to be kept at high precision. Moreover, precision changes are not always the answer. Let's consider this example, where we add a small number to a big number, and then subtract another big number from the result. With FP32, we don't have enough bits to represent that one after the addition, so we get a wrong answer. We can easily fix the problem by using FP64 instead, but we can actually make things work even with just floating point 32. If we reassociate terms like this, we will be able to compute the correct result with just floating point 32. But of course, doing these types of transformations requires knowing the runtime information about our programs. For example, which numbers are big numbers, and which numbers impact the result the most. These examples are just the tip of the iceberg, and there's a whole class of literature devoted to ways floating point computations can be improved. One direction is to change precision in a careful way to speed up computations while maintaining a decent program accuracy. Another way is to rewrite floating point expressions using tools like Herbie. But these tools require a lot of human involvement in the loop. There are also math library functions that provide function-level approximation. These approaches all require human intervention about details like floating point ranges to determine if they are valid, let alone performant. We are trying to answer two questions. Can we automate the existing floating point optimization techniques in compilers? And we hope to find out how much performance we are leaving on the floor by poor choices of floating point precision and expressions. To answer these questions, we built Poseidon, an end-to-end system which automatically transforms floating point expressions in programs to maximize program accuracy subject to a computation cost budget. We implement Poseidon as a PGO-like two-phase compilation within LLVM. In the first compilation phase, Poseidon uses an instrumentation pass to extract program information. In the second compilation phase, Poseidon automatically generates subgraph and expression-level transformation candidates and uses a dynamic programming solver to compute the best combination of transformations that maximizes program accuracy subject to the computation cost budget. We implement Poseidon on top of Enzyme, a high-performance automatic differentiator of LLVM and MLIR, so Poseidon can leverage existing infrastructure to analyze and transform floating point computations in LLVM-IR. Here's an overview of the entire system. Poseidon instruments the input program to produce a profile, and then it identifies floating point subgraphs in the entire input program. Given floating point subgraphs and the profile, Poseidon generates expression and subgraph transformation candidates and evaluates the cost and accuracy of these transformations using a unified metric. After the evaluation, Poseidon uses a dynamic programming solver to solve for the best combination of transformation candidates that maximizes program accuracy. Next, I will go through the entire process in more detail. First, let's take a look at the instrumentation pass. Poseidon compiles an augmented version of the input program by synthesizing gradient code using reverse mode enzyme and inserting logger function calls into the synthesized gradient code. Then Poseidon runs the augmented program to extract information of floating point instructions. Let's take this highlighted line of code, which corresponds to the sine function calls on the right, as an example. Poseidon first synthesizes gradient code using Enzyme. Then Poseidon inserts logger function calls to pass both the value and the gradient of the original instruction to a logging data structure. And after executing the augmented program, Poseidon gets a profile of the program that contains the ranges of instruction values, execution counts, and geometric averages of values and gradients. Let's look at the next pass, subgraph identification. Poseidon needs to understand which parts of the program to optimize. We call the LLVM values that can be optimized by Poseidon, Poseidonable values, which includes basic operations and some elementary functions. Other LLVM values, like loads and stores, are not Poseidonable. Poseidon runs a flood fill algorithm to traverse the entire program by following down instruction operands and uses until non-Poseidonable values are met. In this process, Poseidon also identifies LLVM values that propagate data into or out of subgraphs and labels them as input values and output values. And in our example, Poseidon identifies two subgraphs, one containing sine and the other containing cosine. Now Poseidon starts to generate expression transformation candidates. Let's take a closer look at our subgraphs. There are two output instructions, sine and cosine, that propagates value out of Poseidonable subgraphs. Poseidon constructs floating point expressions starting from these output instructions up to the input values and constants. And then Poseidon passes these expressions to expression rewriters to generate expression candidates. For example, Poseidon can pass the cosine expression to Herbie, along with the input bounds it extracted in the instrumentation pass. Then Poseidon gets several expression candidates from expression rewriters and parses these expressions for later use. Now Poseidon starts to generate mixed precision allocations for each subgraph. Poseidon estimates how much changing an intermediate instruction impacts the final result by using the absolute value of the product of instructions value and gradients that Poseidon captured from instrumentation pass. Given these sensitivities of instructions, Poseidon produces transformation candidates that change precision of the less sensitive parts of a floating point subgraph and inserts floating point casting instructions around the changed region. Now Poseidon has all transformation candidates ready. It starts to evaluate how these different kinds of transformations change the global program in terms of cost and accuracy, using its internal cost and accuracy models. For a cost model, Poseidon either uses the per instruction cost from LLVM target transform info or uses a more precise custom cost model from micro-benchmarking LLVM floating point instructions. For both kinds of transformation candidates, Poseidon sums up the products of execution counts and instruction values for all instructions in that transformation candidate. For accuracy model, Poseidon uses a built-in MPFR evaluator that computes a ground truth value using arbitrary position floats and emulates original computations using regular machining precision. After that, Poseidon calculates the local error by computing the difference between the ground truth value and the emulated results, and then amplifies that local error by the gradient to estimate how the transformation candidate contribute to the global error. Now let's look at the final phase of Poseidon, the dynamic programming solver. Poseidon needs to solve for the set of transformations that generates a minimum sum of global error contributions subject to a user-defined cost budget. Poseidon's problem is really a more complex variant of this zero-one knapsack problem, where we are trying to find the best way to put items into a knapsack to maximize the total profit without violating the capacity constraints. The zero-one knapsack problem can be solved in polynomial time using dynamic programming. The difference is that Poseidon needs to round all computation costs to nearest integers in order to be able to split the original program with a larger budget into many subproblems with smaller budgets. Poseidon also needs to adjust the cost and error contribution of subgraph candidates to account for the expression candidates that are already selected by the solver. So the same piece of instructions won't be modified multiple times. We evaluated Poseidon on FPBench, a collection of micro benchmarks written in a functional programming language. We exported these micro benchmarks to C and used Poseidon to optimize them. We computed the geometric average of runtime improvements across all 46 micro benchmarks that are immediately optimizable. Across all micro benchmarks, allowing a relative error of 0.01% gives a 5.3% average runtime improvements in return. Poseidon can get an accuracy improvement of up to 5 mantissa bits on several micro benchmarks. Let's take a look at one micro benchmark. The dashed line on the top is the runtime of the original program. The dashed line on the bottom is the relative error of the original program. Blue and green dots are runtimes and relative errors of optimized programs. For this micro benchmark, Poseidon offers 6 optimized programs to choose from, including those that are faster but less accurate, and those that are more accurate but slower. Here is the Pareto front of optimized programs. On the lower right of the plot, Poseidon offers 2 programs that are both faster and more accurate than the original program. We are currently in the process of evaluating Poseidon on large proxy applications. That concludes my talk. I introduced Poseidon, an end-to-end system that automatically performs profile-guided two-phase optimizations of floating point programs in compilers. Thank you.
Any questions?
Hi. Can you say a little bit more about the applications that you're targeting? Because I think of the big use of this kind of thing right now would be in machine learning, but if you're not taking quantization of weights into account, then it's sort of tricky. So what applications are interesting? Are these mostly high performance computing, or?
Currently, we cannot really manipulate high-level constructs in machine learning like tensors, but we can optimize real proxy application in scientific computing, like LUESH, which is a hydrodynamics benchmark.
Cool. Thanks.
Yeah, thank you.
When you were specifying the computation cost budget on one of the slides, the numbers were like -6, -5, -2, 0. What do those refer to? Yeah, that slide. What's the?
These are how much runtime slowdown the user can allow. For example, if it's a very large positive number, the user can afford a very large slowdown in return for a better accuracy. If it's a negative number, that means the user just wants the program to be faster. But we can still achieve the best possible accuracy for them.
Okay.
Great talk. Maybe I missed this. Can you comment about the end-to-end compile time overhead of this approach?
Sorry, what?
What would be the end-to-end compile time overhead of this approach? Like how much time you spend in like deciding these
Oh,
subgraphs?
For a benchmark like this, there's one expression in it, and the runtime, the compile time is mostly dominated by how long Herbie takes to optimize this expression. And if Herbie takes like 20 seconds, our compile time is probably just 21 seconds. So our subgraph identification algorithm is pretty efficient, and it's mostly dominated by external tools like Herbie.
Thank you.
I also have one question. I guess you showed one example where you had no runtime penalty, but yeah, I think if you go once back, yeah, basically the runtime is better, and you don't, but still at the 0 line, right? I think you also mentioned that you found a few candidates where you basically don't have to pay with runtime, right?
Yeah.
So would those be like interesting patterns to add to LLVM's existing, say, combiners or something like this? Because you know it's a good pattern you don't pay for, right?
Yeah, if the user can afford the external tools runtime.
No. I mean, if you know this, actually, if you have one expression and you know this transformed form doesn't cost more in terms of precision, but it gives you better runtime, it might be worth adding that to all the existing transformations in LLVM.
Yeah, I think so. Yeah, if we can identify patterns like that, we can definitely add that to LLVM's existing infrastructure.
All right. If there are no more questions, I guess it's time for lunch. And yeah, the staff will direct you to where that can be found. Thank you.